Hello, in this video we are going to speak about regex trees. When we have a list of words to match, we usually concatenate them using a pipe symbol. A pipe symbol is an alternation operator in regex. However, when we build dynamic regular expressions using a list of words that is supplied by some user and we do not know beforehand what these words look like, we need to be very careful. Why? You know that in NFA regex, alternations are processed from left to right, and the first alternative wins, and the others are not processed. However, an alternation group is only efficient when each alternative cannot match at the same position inside the string. If one or more alternatives can match at the same position inside the string, backtracking can come into play and ruin the whole performance. The more there are alternatives that can match at the same position inside the string, the less efficient is the pattern. Now let's have a look at a concrete example. You can see an input string like this: fools, fool, food, fool, foolish, foods. So the initial naive attempt to match these words would be to construct a regular expression based on this list of words that will look like this. And you can see a test at regex101.com that we match all these strings, not as whole words, inside this string, and it takes about 29 steps. However, you can see that the result is not expected, because in the word food, we would like to match food and not foo. That's why we might want to try solution 2. Here, the words in the list are sorted by length in the descending order and put into the regular expression like this. Now let's have a test, and we see that now we matched food, fool, foolish, fully. However, we see that we also matched foo in a foos, and this is not expected. We need word boundaries. Good. Solution number 3. Words are sorted by length in descending order inside the list, and we added word boundaries here. So, in Python, we can build this regular expression using this code. And the regular expression looks like this now. Good. You can see there are correct matches. A foos does not match, but it still takes 92 steps. And you can see that each alternative here starts with the same prefix, foo. You can see it here as well. So this is where regex trees come into play. Have a look at this example here and the test. You can see that it took 67 steps for this regular expression to find all matches in this string. You can see that foo is only tried once. Then we can only try L or D. After D there is an optional S, and after L there is an optional ISH substring. So what is a tree? A tree is a kind of a tree data structure used for locating specific keys from within a set. So these keys are, in our case, of course, strings, and there are links between nodes in this tree that are defined not by the entire key but by individual characters, or in our case, sub-patterns. So this is a tree here for keys A, 2, T, TED, 10, I, in, and in. And a regex tree is a regular expression that is built in a tree-like way. So you can have a look here. How can we build such patterns? Usually, there are such specific libraries that help you create regex trees. For example, in Python, you can use the tree regex library. You can see it here. All you need to do is to install this library using pip install tree regex, and then you can build your patterns using this library in a very simple and short way. However, you can also use other ways to build regex trees, and one of these ways is described in this Stack Overflow answer in a speed up of millions of regex replacements in Python 3 post, which is really very, very nice and highly customizable. Now let's continue with our testing. I have found some arbitrary text in the internet, and it will be our sample input text. In order to make our test more close to real-life situations, scenarios, I decided to extract all words from this text. That's why I'm using this part of code here with refind all, and you can see all the words extracted here. So there are a lot of words, some of them start with the same letters, some of them don't, so this is really close to the situations you might come across in your real life. So we build two patterns. One of them is not tree based and the other one is tree based. We compile them and you can see the patterns here. So tree regex look very cryptic, but in fact that's why they are much more efficient in the end. In this block, I benchmarked the two regular expressions using the Python 3 library. You can see that I ran each of them 10,000 times, and it took the first pattern longer than the second pattern, which means that the tree pattern is more efficient than the regular expression that is not tree-based. Tree-based regular expressions are very efficient to match very, very long lists of words and even such things as emojis. For example, you can see this post at Stack Overflow where all current emojis can be matched and extracted using a huge pattern, but this pattern is still quite efficient when you use it in your code. You can learn more about this construct if you follow the links in this further links section. And if you like my video, please click like and subscribe to my channel if you haven't done it yet. Thank you for watching and happy regexing!